Did
He
you?
promised to.
Well, by the end of the day. Give me till the end of the day, right? What time? What time are we talking about having him done? Right? Like, right? That's what you guys throw.
Yeah. Said I'll have it by.
I'll have it by Monday. I am not done yet. I play the same game you guys play. So is it like 5 or is it like midnight? Like which one is it? Right, I'll get it done. Yep. Okay, so we're talking about composite construction. These are pre-stressed beams with concrete decks on top. Okay. Let's talk about the pros and cons of this. Right. Oh, okay. Before we get into that, we'll talk about this. Down here, let's just draw what we're talking about. So you have these 2 precast elements. Like in the bridge that we did this summer, we just put down 2 beams, and then that is the riding surface. Okay? Sometimes they do that and they're okay with that. Other times they want to put a deck on top. I think Lency said, he's the bridge engineer that designed the bridge we did. He said next time he's going to do it with a composite deck on top. Just so that's then who gives a shit what the UHPC looks like if it's buried underneath the deck, right? So that was kind of, but I was like, it's pretty though, but it didn't turn out pretty. It had all those holes and stuff. But if you put concrete on top of it, who cares, right? And so they'd have these 2 elements that you come in and you put next to each other, and then on top of that you would put a deck, right? There'd be a whole series of these things that going along. Right. Some sort of deck that's placed over the top of it, and there's kind of pros and cons to doing that. And this guy right here, same deal. It would be. This is looking at it from the side. Right? Placing a deck on top. So this would be like 2 beams in a row, and then you have this deck that kind of like runs across the whole entire length. So this upper one's like looking this way, and then this one's looking from the side over here. Okay, and so there's pros and cons to doing this, right? Let's talk about the pros first. Why the heck you would spend time doing this? Okay. Reduced. Right. Conventional methods, I mean not having pre-stressed members that you put down and put deck on top. That's what I mean. Not just pre-stressed. Obviously, if you just put 2 pre-stressed members and then make that the riding surface, then that's obviously faster than coming back and putting a deck on top. But this is like a standard bridge deck, right? Where you have shoring up underneath it, and you put reinforcement, and then you come in and you cast the concrete on top of it. Like doing this type of thing is way faster. Okay. And then it might as well mention, I don't know if we talked about accelerated bridge construction, ABC. You'll see it all the time. Right. That's a big thing in the bridge world these days. We'll talk about it a little bit more when we talk more about bridges, but that's a big thing in the bridge world, is getting it, how quickly can we make this bridge, right? This makes a lot of sense. Accelerated bridge construction is huge in Seattle and in California. And all these places have lots of traffic because you can't just like shut down a road in one of those places. You have to be able to they did it down near the Salt Lake area. They did a lot of this where they do a lot of this where they just come and take the old bridge out, put the new one in as soon as possible. And they're only, in some cases, shut down for a couple of hours. Yeah.
So one question I had even with the Wisdom bridges is what happens when that deck surface wears? Like the UHPC that we use would wear different and stuff, or if you use.
That's a good question.
And if you use composite decks, or I guess if you have the decking, then that part. But if you're just using pre-stressed members, does that wear down differently? And then if you have to resurface it.
That's a good question. Especially so I think typically what'll happen is if that was just a regular conventional deck and then you do that, they can come back and resurface it.
Will they just fill or?
A lot of times they'll grind that top surface off. Yep. They'll come in and dig it up. Yep. Get it down just a little bit, and then they put a deck, like a new driving surface on top of it.
So I just wasn't sure how much you could grind the pre-stress without worrying about.
Right. You got to be careful. Absolutely. And that's one of the things that you're looking at in your research is what is because then if you put down just a conventional concrete deck, you're limited on how small you can have that deck. You have to go a certain distance with regular concrete, but with UHPC, you can probably get away with a little bit less, and then it's going to wear better. But I didn't think about that. The pre-stress, that UHPC is so much stronger than that pre-stress. It is going to wear different, right? And there'll be little ridges there. Hopefully I'll be dead by then, right? But not like, I should rephrase that. Hopefully that's so far in the future that I'm dead. Not that like it happens next week, but I'm dead before then, right? Like the long term. Okay, that's a good question. Jared, what were you saying?
If you ever want a good example of them like shutting down a road in a major city,
Yeah.
in California, and, like years ago, they did this giant, like was the biggest one they've ever done, and they called it Trafficzilla because they had to shut down the 101, which is like the biggest freeway.
Sure.
The 405 actually, and they shut it. It's a huge bridge if you ever go under it, but they shut it down for like 2 days.
And it caused major problems, right?
Well,
But
no, they did it on the weekend.
Okay.
But just the fact that they
did it all in 2 days.
Yeah, they did it all in 2
Yeah.
days, and they had like a live stream of it, and it was
That would be pretty cool.
crazy.
That's cool. And so that's a big deal. ABC's a big deal in like a place like that. Montana, it's a big deal. Why is it a big deal in Montana? Yeah, because we get like 2 weeks of summer, right? Like in some of these, right in the mountain is actually this summer like drunk on. But this year we ran into problems because the wildfires, right? So you get like 2 months of summer, but you get like 2 weeks of clear skies, and then the freaking wildfires come in, and then in this case went right over the top of the bridge. But it's weather, right? How long is our building season? It's actually very short, very concise. Yeah.
I was just gonna say that I saw a New York article, they did it overnight. They would do it.
Yeah.
Instead of doing it during the day, they just have all the lights out, they fill it over through the night and have it ready built
Yep.
the next day.
Yeah. I mean, we're not doing that here. This is the same thing, right? But they do that. Like I know, like in Utah, they did that where they spend a long time building this bridge off to the side, and the bridge is all ready to go. And they come in with like a special truck, and they demo the old bridge, and they lift it up, and they move it out, and they bring the old bridge or the new bridge in, and slide it in, and then put it into place, and then do what they have to do. And they're only shut down for a couple of hours. So like us building a bridge in 3 days. Yeah, but in that case, it was kind of interesting because it wasn't like we built it off to the side and moved it into place. This was like they flew in all these Lego pieces and we connected them all with UHPC. But anyways, ABC, you'll hear it. If you go into the bridge world, ABC is a huge thing. It's all over the place. And sometimes ABC goes bad. That was ABC where that pedestrian walkway collapsed a few years ago. That was all ABC, and they built it off to the side and they brought it in. And the problem there was the moving it and placing it wasn't designed correctly. They're lifting it. They had to pick it from different points than where it was going to be bearing on the other place, and they didn't think through all that sequencing enough, and obviously bad things happen. Positive here, pro cast in place deck acts as wearing surface. We were just talking about that's one of the benefits of having that cast in place deck on top. Shoring can be eliminated. Right, we'll talk more in detail about shoring in a minute, but shoring is you come in and you would have to, like, if this was conventional concrete where this was cast in place and this was cast in place and you had a deck on top of it, you would have to come in and support everything before you cast it. Right? You'd have to have supports all along there for the formwork. So when you cast that deck, when you do it this way, you'd have, obviously you should keep copying these T's either direction. You would have it overhanging like this. But you have these pre-stressed members that you come in and fly and put them into place, and then you put a deck on top of it. You don't need shoring because these pre-stressed members are what's going to be carrying the gravity loads as it's spanning across. And so we don't have to have that shoring, which obviously speeds things up. Formwork for a deck can be significantly reduced. Right? You don't need to have, like usually for a deck, you would have all that, you'd have to have basically a little structure, a wooden structure that supports all of the deck underneath. In this case, you don't need that. I don't know what this. I don't like the E. And this is added slab provides continuity. Added slab provides continuity. Right. What do I mean by that? It just means that like, if I got my truck driving out over here, right, and it's over the top of this, it'll spread some of its load to the member next to it. It doesn't have to carry it all by itself, right? And so this top adds stiffness, which then transfers load into the other beam. And then conversely, if I'm driving my truck along like this, you get lots of dips as you go along. But this member right here can carry tension, and it'll make those dips less as you go across it. This will allow a negative moment to be carried across the top of that dip. And so that'll add continuity. It just kind of ties it all together.
Would it help with cambers too?
Yeah, it would help with cambers too. Yep, it helps with all sorts of stuff. It keeps the cambers down, is that what you're saying? Keeps the cambers down, yeah. Yep.
And even.
Yep. Yeah, right. And then the unlevelness, right, that we were dealing with on that bridge this summer, where, right, you put a cast in place deck on top of that, it can kind of work some of that stuff out. Right. I know they run into some problems because they're trying to cancel out some of those cambers or like dips and stuff as you go along, and so they end up making the slab thicker in certain spots. So if it's going across and there's like a little bit of a dip, then they'll put deeper concrete right there to kind of make the surface a little bit easier, or a little bit better. But the problem with that, you add more concrete, which makes it deflect a little bit more, and so they end up like chasing their tail a little bit because of doing that. Let's say part of this is continuity. We get, let's see. I want to add a couple things here. Reduce vibrations. Less vibrations on the bridge when you have that continuity. Reduced end rotations. Right? As you're moving along that beam, you get less rotations, right? Smoother. Spans. Smoother transition between spans is tied to the reduced rotations. Protects from, well, I'm going to add that to, I'm not going to have that underneath there. I'm going to have that as an F. Protection. Right. If you've got, oftentimes these joints right here, oftentimes those joints they've got steel that kind of spans like this. Right. They have steel that sticks out, and then they come in and cast and stuff. Usually there'd be a gap. I didn't draw this right, but there usually would be a gap between the different kind of glue together afterwards. But they have steel that sticks out into that gap. And then having this on top, if it's done right, will protect, chlorides and stuff like that from making it in there. Water chlorides from making it in there. Yeah, there should be like a little gap in here. Tie them together. And they don't put them right up next to each other. This is what we were talking about before. They actually don't allow these on bridges, federal highway bridges anymore, just because these are kind of sloppy out there, flopping around out there. So they don't let you do those anymore. They get all sorts of cracking associated when they do that. So you don't see that too much anymore.
I have a question about that.
Yo.
So when they place those, how do they keep them from tipping over? Because those are single T's, right?
Yeah, those would be single T's. I think what they do, something. That's what I was trying to draw here. They do like a coat end on it, right? So they don't have it. They'll like terminate the web when you get close, and so then you can kind of like bear on the top of it, right? That's what they would do. Yeah, you're saying like if you had a double T sitting on there, right? But I think they do something like this, where the beam right, and then they stop the web, and then they let the flange stick out, and then they bear on that flange there. Obviously, there are design considerations when you do that.
I was gonna say, because that would obviously reduce
Yeah, it reduces your shear strength near the end and stuff like that. That's what we said. One of the places that shear can control is if they do that, right? They reduce it, but then also your shear demand is a lot less there. I was gonna try to draw a truck. I'm gonna use can't even draw a circle. Let's see what we got here. Nope, can't draw a circle. Truck coming in. Doing okay. Oh, this is probably one of the best trucks I've ever ridden in, drawn in my life. Hells yeah! Look at that shit. That's no. Door. What does the door look like? All right, I'm gonna give it that. I'm gonna go with that. Does it have a door? I want to see your trucks. I do. I really want to see your trucks. Let me see your truck. Anybody draw a truck? Let me see your truck. I always feel bad about my trucks. What's yours? Hey, I made something of mine. You copied me. Oh, yours is better. Oh, yeah, there's. Yep, you got the lines in there. I always feel like, that's not bad. That's not bad.
Mr. Brian.
All right, keep going. Yeah.
There you go.
Oh, Daniel wins. That's a nice one, Daniel.
Yeah.
That's good. I like that one.
You good?
Yeah, I do. Yeah, let's see. Guess what else just come out? Oh, that's pretty good. You got a little more detail. I always feel like I said, I feel self-conscious about my drawing. You didn't even try it. You got nothing? Well, come on.
Come on, son.
Well, you just copied me too, man. See, that's why I used to feel really like self-conscious about my drawings. Like, oh my god, I'm gonna draw this truck and it's gonna look silly, and then people are gonna make fun of me. But then I'd look at your guys's, and yours just as bad as mine. And so I'm like, oh, I will not feel guilty about my drawing, or I will not feel bad about myself because I can't draw a vehicle.
Have you ever seen a truck with the wheel right by the windshield?
Why is the windshield wrapping?
You didn't even
around-
draw one, so you can't even make fun of me, bro.
Why is the windshield wrapping around to the side of the door?
I don't know. That's just, isn't that weird how like our brains don't work this way? Some people like just like, oh, let me just draw this really quick, and then this looks really pretty and stuff, and then like I was like, God, what does a truck look like again, right?
Window.
And then that's the other problem too. The harder you try to draw the right thing, the harder, the worse it turns out, right? That's the same thing with my handwriting. If I'm like, okay, really concentrate, make your handwriting as clear as possible. It doesn't work that way. It doesn't work that way. Okay. Cool story. You're getting into some deep stuff there. Cons, what do you think the cons are? Cost, right? Cost more.
So composite is just regular concrete on top of.
Yeah, in this realm, if you hear the word composite construction in pre-stressed concrete, that's what they mean, right? And that's what we're saying is, depending on the field, composite construction means all sorts of stuff, right? Composites and carbon fibers and steel decks on top of it. But in pre-stressed, usually that's what it means by composite construction. It's just a precast element with a concrete slab on top. Yep. And this is actually interesting. B. I don't know. This isn't necessarily just a con of composite construction. This is more for, I'd say this encompasses just pre-stress in general, or precast in general. Right? Moving the elements is a big deal, right? You're limited how long you can go, right? And you got how high you can go, obviously, right? You got to be worried about that, right? And I think that we showed you pictures before. They had like these trucks. All their beams from that bridge this summer came out of Idaho, right? Is it Boise? Is that where it was? Outside of Boise is where they came. And then they had these special trucks where they had the front end of it and a pivot, and then the back. The beam was just the trailer itself, and it spanned back, and the back end was on wheels as well. And they would move that around. Part of that was so that when they unloaded it, a crane could come up and lift part of it, and then they could move it around with the crane, and the truck would back up even closer, and then the other crane could come in and pick the other half of it, and the two of them can swing out their stuff. But they're limited in how long they can get. Let me see, I got a YouTube video. I don't watch YouTube videos very often.
Goodbye, Roman fees that rack up overseas. Hello, automatic coverage when I'm exploring the world. Hello, Google Fi, a phone plan that can.
In this case, they wouldn't be. In this case, they're doing composite construction, but they're not connected. They wouldn't have something to be set up with that. Casting bricks that don't have scanning across. I thought that was interesting. Obviously, so that's my transportation. That's just one beam. Yeah, that's just one. Yeah, there's got a bunch of them coming. Okay. Issues and concerns. We already talked about shored versus unshored, right? So the kind of the benefits on the shored construction, smaller sections, right? So what happens is when you have the specimen underneath, if you come in and you place shoring along the length of that beam, even if it's precast construction, you can still put shoring, meaning you're just supporting the elements as you go along. And then you're casting this wet concrete on top of the beams. And if it's shored, you can get away with having smaller sections because it doesn't have to carry that wet concrete, right? If you have unshored, the beam has to carry all of that wet concrete. They have to carry all that slab. Once that concrete sets, then it's going to act compositely and add to your structural properties, right? It's gonna resist the load when you come in and put load. Once it's set, it's gonna do that. But before it's set, it's just weighing down your beams. So your beams have to be bigger to carry that wet concrete. Right, no need to support full weight of wet concrete. Okay, unshored, right, or no shoring. Oh yeah, maybe unshored is not a word. No shoring. And no disruption of traffic. Right, that's one of the benefits. It's just spend more time on shored versus unshored, but there's kind of the highlights from what I used to talk about. Is that you get smaller sections if you do shored, but shoring it's going to take longer because you have to have add your shoring along the way. It can disrupt traffic underneath if it's like an overpass or something like that. So if you can avoid shoring, that'd be great, but there's a penalty to that. You'll end up with bigger sections. Different concrete strengths and stiffnesses. This comes in for sure. This is a big issue. Right? Deck is typically a conventional concrete, which is 3 to 4 KSI, right? Whereas your pre-stress beam has above 6 KSI. And so they're different strengths. Concrete, which means they have different stiffnesses, right? Right, stiffer as well. Pre-stress beam, make that more clear. And because of this, we have to use transformed sections. Remember that? Remember method of transformed sections? You guys doing that now-ish, right? Did you do that in advanced mechanics? No, not yet. You do it in regular mechanics of materials, remember that? We have like union of two materials, you kind of fudge it so that you could use MY over I, right? So we actually have to do that here. We don't have to, but we do that here. We use method of transformed sections to solve these things because they have different strengths. A little foreshadowing of what's to come.
Who decides if you're going to do shoring?
I think the engineer. They make the decision. Sometimes maybe shoring is not possible, right? So that might make it so that maybe you can't, maybe it's over a river or something like that. You're not going to put in temporary shoring. Maybe there's like traffic underneath, so you're not going to do it. But I think the engineer makes that decision, right? It's up to you. It's weird. They give the engineer lots of power. Yeah, right? Like, when I was talking to Lensley, it's just like, it's just what the engineer decided to do. We have pre-stress members like, do you want to use a topping slab or not? I don't know, let's not do it, right? Like, or let's do topping slab, or like maybe the guy you work for is like, I always do topping slabs, or I always do shoring, or I always do this. So that's just the way we're going to do it, because that's the way I like to do it. Right? Give you a lot of power. Give you a lot of power. So yeah, I don't think there's no. Like I like to think that there's like this rule book that you follow and use, right? Like, yeah, right? Oh, this is for this thing. Like, what type of bridge do you use? Do you use steel underneath? Do you use pre-stress underneath, right? Oftentimes they bid it out as both. The MDT will bid it out as steel, like, and then or they'll bid it out as a pre-stress, and they kind of come back and say which, let the engineers, designers out there decide what it's going to be. Yeah. Because they got to see how much it's going to cost. Sometimes they put it all out, and then the contractors come back saying, I can do steel way cheaper, I can do pre-stress way cheaper and stuff, right? All the decisions on like, why do you make your concrete or your building out of concrete versus out of steel versus out of, right? Who knows, right? It's just what the engineer just decides to do along the way, right? Or even the contract, or sometimes the architect would make that because it makes it feel a certain way. Like we don't want steel because it's, we used to, in one year I taught grad level courses, there was a guy in there whose undergraduate degree was in architecture, and then he was getting his master's in structural engineering. We had a lot of fun with him. Just like we'd do our tours and we walk in, it's like, so Scott Bean's his name. Scott, how does this building make you feel? Right? Like, does it feel? Oh. But I make fun of architects, but absolutely they make a difference in a building. Cobley Hall, Norm Asbjornsen Hall, right? Like, right? You walk into Norm and it's just like, right? It's just such a good feeling. You can see the outside. You can see the outside over there. That you walk into Cobley and your soul leaves your body, right? It's like it just goes, oh God, right? Tate Lab, your soul's like, I'm out of here. I ain't going anywhere near Tate Lab. Did you guys spend a lot of time in Tate Lab as undergrads? It's kind of fun, right? Just hanging out with your buddies. Just what's that? Yeah, windowless room in the middle, so you don't know what you're missing outside, right? Then you walk in here. This is a nice building. Look at this. Windows, right? No eyebrows over the windows like Cobley has. Right? You know what I'm talking about? This little, who are you, architect? You know what these windows need? Eyebrows. Every one of them. All 6 floors. Every single little teeny window gets an eyebrow. Yeah, so much better.
Not as restrictive view out the window.
Yeah. You're already restricted window. I brag that I could literally see 6 brick walls from my office. If I look out my office, I can see 6 separate and distinct brick walls. Beautiful. Makes me feel so nice being in there. All right, so the part C there. This also adds complications. This is an issue with designing these things. The pre-stressed beam, or precast beam, is pre-stressed and the slab is not, right? So how do we handle that, right? One of them has these internal pre-compression stresses, and then you come in and you put a slab on top. And we'll talk about what controls here, but you think about it, right? What it's gonna do is add, oh, that looks like a face. Right?
With eyebrows.
With a unibrow. Anyway. Just check. Okay, so we're adding in some load stages, right? You have your pre-stressed member, you come in, right? So let's say it's a precast element. You come in and you have a concrete, you take your steel, you stretch your steel, you cast your concrete around it, you slice it, boom, it shrinks in, pops up, okay? Then you take that out within a couple of weeks possibly, bring it out, put it on a job site, set it down there, good to go. It's just kind of sitting there with a big camber on it, right? Because it's kind of being popped up. It's in that state right there. But some time may have passed, and during that time that's passing, what has happened to your FP? Is it the full pre-stressing, right? Is it reduced a little bit? Have we gotten some pre-stress losses at that point? So you gotta think about that a little bit. And then you come in, you put this wet concrete deck on top, right? And so now your beam is gonna be loaded up with this wet concrete deck. Those beams have to carry that whole deck all by itself. Okay, so that thing's carrying the whole deck, right? You gotta make sure it doesn't fail in that condition. But then after it solidifies, right, or hardens or cures or whatever, that concrete deck now becomes part of the beam. So now it's part of the beam. And so then when you put your dead loads on top of it and your service loads on top of it, when the two bend, they bend together, right? The compression, right? Your slab up here goes into compression, right? And then this guy's got, compression and tension in it. It's got pre-stressing in it to begin with, but then now it has the extra load. That extra load now has got to have different section properties because now it's got that beam on top of it, or the slab on top of it that's helping it out, right? It gets interesting, right? That slab on the top doesn't have to carry any of its own dead load. All of its dead load is in those slabs, is in those beams. Okay. Anyways. We're going to get into detail there, but that's just to tell you what's happening, right? There's a lot of shit going on when you do this, right? But handleable, able to handle it. Okay, so I guess pre-stress members, what to use is effective width. Remember, I think if you take an advanced concrete, right, I get to count this slab up here as being part of my beam, right? It's part of the beam, but how much of it do I use? Do I go, you can't use all of it. I can't go all the way here and all the way over here. There's an effective width that I can use, right? Be effective. How much of it does get engaged, right? And so when we say effective width, to say how much could be used, that's called BE in the code. An equation for BE, be effective. How much of a slab will act compositely? Okay, that's what we mean by the effective width. Okay, and the other part is shear transfer. Okay, when I talk about shear transfer, I'm talking about horizontal shear. Right, so if you have two elements and you bend it down, so this would be spanning. This is spanning across like this, and you put a load in the middle. There's horizontal shear. The top one wants to slide past the bottom one. Right? You bend it down. This one goes through more curvature than that one, so there's the other way around. The top one goes through more curvature than the bottom one, and they kind of separate. Right? They want to slide past each other. You can feel that if you take two pieces of paper and bend them, you'll see that they slide past each other. Okay? And again, what I mean by the horizontal shear it's this aspect, right? We always are worried about that vertical shear, but oh my gosh, my straight line tool doesn't work when you're drawing at a weird angle. That stress block, it's this top one that we're worried about. And the bottom one. Right, so there's some differences. So that, what the hell, this thing's killing me. Okay. And so we have to account for that sliding past each other. And that's why they have those studs on top of it that we just saw in that previous video, right? You put in these, the top part of the beam, you just have these little studs that stick out, a rebar that sticks out, if you will. Right? And what that would look like over here. Right? Sometimes it's done with rebar, sometimes it's done with these little headed shear studs. Right. Can be done in two different ways, but you have to provide some sort of reinforcement like that. And so there is, when you do composite construction, there is shear design. We have to worry about like the shear capacity of these beams, right? But then you also have to worry about the horizontal shear. And so there's a section for horizontal shear design, and what you're doing is you're figuring out how many of these studs, what size those studs need to be, how many of them you need, and then at what spacing they are along that length. So we have to provide that, a mechanism for transfer. Sometimes just the bond between the concrete deck and the pre-stressed member is enough. Sometimes it's not. Sometimes you have to provide steel. So we need to provide mechanism for transfer. So you can rough surface. Sometimes it's a rough surface. Shear studs or rebar. And so there's a section of the code that deals specifically with that. We'll look at it, we won't use it. We got enough stuff going on. Okay. So we'll go over to elastic analysis. We'll introduce this idea of, it'll be good. We have enough time to talk about it. We'll introduce this idea of transform sections and why you need to do it. Okay. This is hopefully I'll explain all that stuff. All right, so we have a transform section. So this is, we've got a pre-stressed member underneath, right? And it has a certain, at this point, we're gonna ignore all the pre-stressing, right? The fact that this thing's already under stress. So this is after, this is just the loads. Oh, this is gonna be, let's write that down. External loads. Composite. No pre-stress. Yep. Make that clear. That's what this is going to be about. So ignore the pre-stressing. We've got a beam that has a certain stiffness and a certain strength in concrete. We put on a slab on top of it that is less stiff and has a lower capacity, right? Over here is the stress strain diagram of the two concretes. So this is the stress strain response of the slab, of the blue there, and then the black right here is the stress strain response of 2, which is the pre-stress member, right? It's stronger, it's stiffer, and then the slab is less stiff, more flexible, and weaker. Okay. You're right there. Oh God. Good way to start it. Good way to start. I wasn't done yet. This is gonna be 1 plus 1. No. So, shit. What is up? This is where it's just off right here. Yep. That's the 2. That's a 1. Uh-oh. Uh-oh. Okay. We'll spend more time on this the next time. Just give me 4 minutes to talk about it. So, okay. So here we are. I did the straight concrete. So what we do is we've applied loads to the 2 different straight of concrete. They both bend together, right? They're tied together. We assume that they have the same strains. They go through the same curvature, and therefore they have the same strains. And then we assume that the plane sections remain plane and they're uniform like that. So that's what the strains look like. Okay? But then the stresses are going to be different between up here and down here, right? Because they're different strain concrete. So you get different strains, you get different strain concrete. So what we do is we come over to this curve right here, and we say, all right, at the first strain right here, we'll call this strain B, epsilon B. And we'll call this up here epsilon C. Well, I'm going to call that, yep, that's fine. Different strains. So if we go to epsilon B, come over here, I'm going to draw epsilon to B, and it'll be, say it's right here. Right, so this right here is epsilon B. Okay, so given this strain right here, at epsilon B, my slab is right here, right? It has a stress less, but then my beam has a higher stress, okay? So what this is, we'll call this right here sigma A, okay? And I'll call this right here sigma B. So what this is, this right here, sigma A, and this right here is sigma B. Right, that's why there's a jump. Because right here at strain B, I have a less stress here. Sigma A is right there. And then this one right here is a higher stress. So it's right there. That's why there's that little kink in it right there. Because it's one concrete has a higher stress versus this concrete, the beam has a higher strength, and the other one has a lesser strength. Okay? And then you go out to what I called strain C. Strain C would be here. Right? And the only thing that's out there, the pre-stressed member is ended. And so we're right there, which we want to call sigma C. And so this right here is sigma C. That's why the stress distribution looks the way it does, right? Because the stiffer one gets more load, right? The stiffer one, for a given strain, it gets more load. The more flexible one, that same strain gives you different stress, okay? And so then, I mean, you could actually calculate it like this. You could go through and figure out what those stresses are. Once you know those stresses, then you can calculate the moment, right? You can come in and say, all right, this guy has, you know, this triangle right here has a resultant force right there, and that one has right there, and this one has one up here. And you can calculate it the hard way. You can absolutely do that. But the whole point of the method of transform sections is what we're going to do is we're going to pretend, right, this slab has low, right, so up in the slab it has lower stresses. So what we're going to do is we're going to pretend that this thing is narrower than it actually is. If we pretend that it's narrower than it actually is, then these stresses go up, right? You pretend that that's narrower, so then those stresses aren't low anymore, those stresses go up. And then what it enables us to do is treat it as if they're uniform like this. So that it looks like that. Right? And we'll cover that next time, but it allows us to do that. The reason we want to do that is though we could use this relationship right here, my over I. It's way easier than doing it the way that we were talking about before. I could calculate the moments, I could figure out what the resultant forces are, I could figure out the moment arms, I could do it, right? But then it's just more complicated. I want to use my my over I stuff just because it's way easier, right? And then and so what we do is we pretend that thing's a little bit narrower. I calculate the properties by pretending that, or I pretend those are narrow. I figure out what the moment of inertia is of the beam with the narrower width. And once I do that, that's what this I is right here. I treat it like this. I go through all my calculations, and at the very end, I have to transform it back to what it actually is, and there's like one little step for doing that. So we have to do this. Okay. Anyways, that's enough for now, and then we'll keep going with those notes. We should figure composite or finish composite construction next time, and then Friday we'll have post-edge floor design. Break.